Okay, I'll get started with today's class. Just, of course, a brief reminder that on Thursday we got test 2. Test 2 has that same format of multiple choice, numerical answer, long worked out problem as test 1. Test 2 content is the material since test 1. So it's chapters 19, 20, 21 is material on magnetism, on induction, and today's class where we're going to combine together electricity and magnetism. Any questions on the arrangements or the process or the details of test 2? I'm looking in chat and it looks like a vacuum in chat. Oh, there is. Are you going to post a solution video for the practice test? Yeah, I will tomorrow post either a solution video if I have the energy, or a solution written out paper if I have less energy. So one of those two things will get posted and get posted tomorrow. Okay, I'll get started with today's material then. And if you have remaining questions with the test, questions about the test, you can ask me at the end of class, or you can ask me in an email or however you like. Okay, I see my video of test 1, practice test 1 was popular. So that is actually encouraging me to somehow get together that energy to make a second video. Today's content, today's class. Today's class, I want to talk about a very, very important event in physics and science. And this very, very important event in physics and science was the unification of electricity and magnetism into what we call electromagnetism. It was the joining together of our understanding of electric forces and our understanding of magnetic forces into a single common electromagnetic force. So it's a huge, I can't understate, I really honestly can't understate the importance of this event. One of the important things that emerged from this event of joining together electricity and magnetism was a prediction of a new type of wave in nature. Now, it wasn't like a water wave or a sound wave, it's an electromagnetic wave. And it was a realization that, for example, sunlight is actually an electromagnetic wave. So it was a sudden understanding of sunlight and other forms of light as electromagnetic waves. Okay, so let's get on with unification of electricity and magnetism. I call it a James Clerk Maxwell special because it's James Clerk Maxwell that was forefront on the unification of electricity and magnetism. It's James Clerk Maxwell's theory that is electromagnetic theory. So it was his greatest achievement, and it was a really great achievement. And as I say, one of the things that emerged from the achievement was a prediction of electromagnetic waves. Now, let me just give you an idea what they are. You know about electric fields conveying electric forces. You know about magnetic fields conveying magnetic forces. Well, an electromagnetic wave is actually a bundle a kind of self-sustaining, self-propagating bundle of electric fields and magnetic fields. And this self-sustaining bundle of electric and magnetic fields can actually carry energy with it, can actually carry momentum with it, like a particle can carry energy and momentum. And so this was a huge breakthrough. To understand, imagine suddenly you understand what sunlight is. That seems like a huge breakthrough. So there were a couple of clues floating around at Maxwell's time as to a connection between electricity and magnetism. And I've got 2 slides here on these 2 clues. We're just going to review these 2 clues, these 2 slides. And these are the 2 clues that clued in Maxwell to joining together electricity and magnetism. So here's the first one, and it's pretty straightforward. So I'm comparing on the left-hand side here, electricity, with magnetism over here on the right-hand side. And as we know, electricity is a interaction between electrical charges that's carried by electrical fields. And that actually the fields, the lines of field begin and end on positive and negative charges. So that's electricity. And as we know on the right-hand side here, magnetism, well, that's a force between moving charges that's carried by magnetic fields. And we think of moving charges, currents, as causing loops of magnetic field. And right away here, you see a bridge or a connection or a link between electricity and magnetism. It's charge that's responsible for the electrical interaction. It's moving charge that's responsible for the magnetic interaction. And so charge itself, that dimension of nature that we call charge and introduced in the very first lecture class, that really is a bridge, a connection, a link between electricity and magnetism, because charge, moving charge, is ultimately the source of electrical interactions, magnetic interactions. Second clue that there's a link between electricity and magnetism was induction, the effect we didn't discuss in the last few lecture classes. So I've, in this slide, shown you an example of induction. It's when you energize a solenoid or de-energize a solenoid. As you energize the solenoid, de-energize the solenoid, you're switching it on, you're switching it off. In a neighboring coil of wire, a neighboring loop of wire, at those moments when you energize, de-energize, you get little bursts of EMFs and induced currents in that neighboring coil, in that neighboring loop of wire. Well, that's another bridge between the worlds of electricity and the worlds of magnetism. So you're switching on and off a magnetic field. You're turning on and off a magnetic field. And those moments you turn it on and off the magnetic field, you get little electrical signals. You get electromotive forces in your circuit, in your loop of wire. You get electrical currents in your loop of wire. And so that also is a bridge between electricity and magnetism. Well, what Maxwell did was postulate or hypothesize 2 kind of new ways, 2 new mechanisms for creating or manufacturing electric and magnetic fields. And these 2 new ways are pictured I'm not going to give you any equations here. They're just pictured on this overhead. So this is a key slide. This is what Maxwell came up with. This hypothesis of Maxwell. And the basic idea is that he hypothesized that not only can you make electric and magnetic fields with electrical charges and moving charges, but you can make electric and magnetic fields by varying in time magnetic fields, by varying in time electrical fields. So it's a new source beyond charge and moving charge of electric and magnetic fields. So specifically, what I'm going to call magnetic induction is when a time-varying magnetic field, so that's what I'm trying to denote here by this little equation, that delta B over delta T is not zero. The field, the magnetic field is changing. Whenever you have a time-varying magnetic field, it induces, it creates loops of electric field. And that's this picture down here. This picture is indicating a magnetic field. The magnetic field lines are in green. And we're imagining that that field is changing. So maybe it's getting stronger, or maybe it's getting weaker, or maybe it's even changing direction. When it's getting stronger, weaker, or changing direction, it creates loops of electrical field. And that's what we're picturing. So that's a new source of electrical field beyond charge. And then in Maxwell's theory, there's also a counterpart. I'm going to call it electric induction. So in electric induction, you've got a time-varying electrical field. That's what I'm trying to denote here, that delta E, the change in electrical field, by delta T, duration of time, is not zero. So that's an electrical field that's changing. And electrical fields that are changing create magnetic fields, loops of magnetic field. And that's what's pictured in this sketch. So in orange are lines of electrical field, and maybe they're getting, that field's getting stronger, maybe that field's getting weaker, maybe that field's changing its direction. So that field is changing, and whenever it changes, it creates a loop, it creates loops of magnetic field. And so that's electric induction. These two new effects, the one I called magnetic induction on the left here, that actually explains transformer induction. It's a deeper understanding of transformer induction. This one on the right here, that I called it electric induction, it's the counterpart. That's a completely new effect, completely new phenomenon that's postulated by Maxwell. And so these were the new ingredients in his theory. So let's add in those extra ingredients into our old theory of electromagnetism, and let's examine this famous consequence of an electromagnetic wave, prediction of electromagnetic waves. So now, I like this. I'm kind of proud of this slide. It's my picture book version. There's no equations on this slide. It's my picture book version of Maxwell's complete electromagnetic theory. And this picture book version is indicating the 4 distinct ways that you can create electric and magnetic fields that convey electric and magnetic forces. So this is a picture book telling you how you can make an electric or a magnetic field, all the possible ways you can make an electromagnetic field. Well, there's familiar ways. Upstairs here, let's call that number one, right? A charge creates a surrounding electrical field. And upstairs on the right here, a current moving charge creates a surrounding magnetic field. Those are ways when we talked about electricity as a force on its own, magnetism as a force on its own. We met those ways of creating electric and magnetic fields. And now we got 3 and 4. These new ways that you can create electric and magnetic fields. You can create electrical fields with time-varying magnetic fields. You can create magnetic fields with time-varying electrical fields. So this is complete electromagnetism. If nothing changed in time, imagine living in a frozen world, right? Frozen universe where nothing changed in time. The only sources of electric and magnetic fields would be items or pictures 1 and 2, that electric charges and moving charges create electric and magnetic fields. But as soon as you go from that frozen world of nothing changing in time to a more exciting and dynamic world where things do change in time, you get these new ways of creating electric and magnetic fields. And that's the, that's the world that we live in, where things change in time. So this is the complete electromagnetic theory. Well, out of that theory emerges this incredible prediction of electromagnetic waves. Now, I'm not obviously going to work through the mathematics of how the electromagnetic wave is predicted. Probably in part because I'm not sure I could work through all the mathematics of how the electromagnetic wave is predicted, but I want to convey the idea, the concept of how it's predicted. So again, an electromagnetic wave is this really weird, peculiar thing. It's a self-sustaining, so it keeps itself alive. It's a self-propagating, it travels on its own, a bundle of electric and magnetic fields that carry with them energy and momentum. So that's what an electromagnetic wave is. Now how can you make it? There's 2 distinct ways you can make it. Over here on the left, over here on the right. If I took a charge, so supposing right now in my fingers here, I got a charge, some nanocoulombs of charge. If I vibrate that charge to and fro, now that's creating in the neighborhood of the charge changing electric fields. And now we know that changing electrical fields create changing magnetic fields. And that unleashes this bundle, self-propagating, self-sustaining electromagnetic waves. So by vibrating this charge here, I'm creating a stream, you can't see it, but I'm creating a stream of electromagnetic waves that propagate outwards and carry energy and momentum away from me. So it's a fantastic thing. There's a second way you can do it. Supposing you took a current and I flowed a current up and down a wire, oscillated it up and down a wire. Well, that current creates a surrounding magnetic field. That magnetic field is changing in time. And that changing magnetic field will create an electrical field. And again, that creates this self-sustaining bundle of electromagnetic fields that propagate away from the vibrating or oscillating current into space, carrying energy and momentum with them. And so this was another picture I was semi-proud of, that by taking a charge and vibrating it, by taking a current and oscillating it, we can make either a time-varying electrical field or a time-varying magnetic field. And those things time-varying electric, time-varying magnetic fields are this catalyst that kind of ignites this explosion of electromagnetic fields that propagate away, carrying energy and momentum away. Well, that, as you mentioned, that was a huge theoretical prediction. But not all theoretical predictions are fact. And so, like any theoretical prediction, scientists wanted to test the prediction. Heinrich Hertz was the scientist, the experimentalist, was the first person to generate in the lab artificial electromagnetic waves, and the first person in the lab to detect those artificial electromagnetic waves. So this is an astounding achievement. He went on to do a lot of things with these electromagnetic waves. You may know that, well, I mean, some of this I know you know. You may know that light gets reflected from things. It gets what we call refracted from things, from glass, and it gets diffracted. We'll talk about all those things later on in the course. He discovered that the waves that he made in the lab, the electromagnetic waves he made in the lab, which we call radio waves, that those waves also are reflected, refracted, and diffracted, just like light. And for all this work, I mean, he was a fantastic scientist. We use a unit called Hertz for measuring frequency. And we use frequency when we talk about waves. We use it when we talk about electromagnetic waves. We will use it when we talk about sound waves, or when we talk about water waves. But frequency is named after Heinrich Hertz. Okay, so I want to show you a demonstration of the generation and detection of electromagnetic waves. And this demonstration is really how Hertz generated and detected electromagnetic waves. I've got a little slide here to give you an idea of how it works. So that's on this overhead here. What you're going to see in the video is I've got a device, I would call it an oscillator. And it oscillates charge on this antenna here. So this vertical bar here is an antenna, and it's going to be the source, the origin of the electromagnetic waves. And this oscillator makes one end of the bar positive, the other end of the antenna negative, and then flips it, and then flips it again, and flips it again. It's going to do that very fast. It's going to do it faster than you or I could do. It's going to do it at 88.5 megahertz. So it's 88.5 million times a second. The oscillator is going to oscillate the charge. It's also oscillating current, right? If this top end is going to be positive and this bottom end is going to be negative, well, positive charge has to flow upstairs and negative charge downstairs, and vice versa as it oscillates. So the oscillator is oscillating simultaneously, actually, both charge and current. And so it's creating, surrounding the oscillator, time-varying electric and magnetic fields. And those time-varying magnetic and electric fields create more magnetic and electrical fields. And that's the self-sustaining bundle that we call an electromagnetic wave that propagates outwards, that flows outwards, carrying energy and momentum from the antenna. And so that's what we're going to see. So let me share a different screen. And so I hope you can see my Canvas page and the video I made. Now, what you're seeing on the desktop here is in the center, this is the oscillator. This is Heinrich Hertz's oscillator from 150 years ago. We're very lucky to have it. And it's going to oscillate charges and currents on the antenna. You see the left and right arms of the antenna here. And then you'll see it in a moment. I've got another device that's completely separate from this generator of electromagnetic waves that I'm going to use to detect the emerging electromagnetic waves. Okay, so I'm pointing out the antenna just in case you didn't see it or you didn't hear me explain it. And as I say, in the middle is the oscillator. And there's a switch, and I'm going to turn the switch on. And we'll get the thing oscillating. So when I turn it on, first I'm going to show you the detector. The detector is nothing other than a copper bar with little lights mounted on them, little incandescent lights mounted on it. It's completely disconnected from the transmitter. I'm throwing it over there on the bench. It's not connected to it at all. Now I'm turning on the oscillator, and look at the oscillator glow. I can just imagine this in his lab. And now I'm going to bring up the detector, and let's look at the lights. Look, the lights are now lit. Now, they're not physically connected to Hertz's oscillator. They're disconnected from Hertz's oscillator, but they are seeing the electrical fields in the electromagnetic waves, and that is lighting them. I'm going to turn the lights off now. I'm trying to find that device. I'm bumping around in the dark right now. And when I do find it, I'll come back. Here I am. Look, you see those two little lights? Those are the little lamps that were on the detector. And again, it's not connected to the generator. It's out there in empty space in the neighborhood of the generator, yet it's detecting the electrical fields in those electromagnetic waves. And that's Heinrich Hertz's experiment. Let me go back to my slides. And let me, now that we've discussed this feature of electromagnetic theory, that there's electromagnetic waves, let's walk through some of the characteristics or properties of electromagnetic waves. So that's the next handful of slides. Okay, so we've said that electromagnetic waves are bundles of electric and magnetic fields, self-sustaining, self-propagating bundles of electric and magnetic fields. Let's see if we can get a bit more quantitative about the nature of those electric and magnetic fields in an electromagnetic wave. And so that's what I'm going to do over this series of slides. And this first slide concerns the direction of the electric and magnetic fields. They're oscillating electric and magnetic fields inside the electromagnetic wave. And I'm picturing downstairs here an electromagnetic wave that's traveling from over here on the left. So imagine it starts over here on the left. Imagine there's like a flashlight over here on the left. Not a very good flashlight, I know, but it's the best you're going to get. And out of the flashlight is coming light, an example of electromagnetic wave. And that light, that example of electromagnetic wave, is propagating from the left to the right. And this arrow is indicating the direction of propagation. And the velocity of light, for some obscure historic reason, is called c, not phi. And so c here is the velocity of light vector, and is pointing in the direction of propagation of the light, and its size is the speed of the light that's traveling from the flashlight. Now, we've got some, in this slide, you've got to imagine you've got some sort of magic glasses that we bought at Walmart that allow us to peer in the light ray and actually see the electric and magnetic fields. So inside the light ray here, you're seeing in orange the oscillating electric field. And you're seeing it oscillate up and down as the light ray travels from left to right. And in green, you're seeing the magnetic field. It's oscillating to and fro, into and out of the overhead as the light ray travels left to right. And this cartoon is showing you the key feature, important feature about the directions of the electric field, magnetic field, and traveling of the light ray. It's that E, B, and C, so E is the electric field, B is the magnetic field, and C is the direction of propagation, or the velocity vector. They're all perpendicular to one another. And so that was actually a key prediction from Maxwell's electromagnetic theory, that E, B, and C are all perpendicular. So in this case, right, the light ray travels left to right. The electrical field oscillates up and down. The magnetic field oscillates into and out of the overhead. And those are three mutually perpendicular directions, right? So the electrical field is perpendicular to the velocity, the magnetic field is perpendicular to the velocity, and the electric and magnetic fields are perpendicular to each other. So that's a very important feature of light, and in all electromagnetic waves. Well, about the magnitudes, the sizes of the electric and magnetic fields in the electromagnetic wave. Well, here's another prediction of Maxwell's electromagnetic theory. The electric and magnetic field strengths are related to one another and related actually to the speed of the light ray. So the strength of the electrical field, let's imagine the maximum of it. So the maximum is, the maximum value of the electrical field, somewhere up here and somewhere down here. And the maximum value of the magnetic field here and over here. The peak, that is the peaks of the electric and magnetic fields. The ratio of the electric and magnetic field strengths is actually equal to the speed that the light ray travels at. So the magnitude of E divided by the magnitude of B equals C, the speed of light. And that's another key relationship between the electric and magnetic components of an electromagnetic wave. So that's really important too. As I say, these features about the directions of the electric and magnetic fields and the strengths of the electric and magnetic fields and electromagnetic wave, they are predicted by Maxwell's electromagnetic theory. Okay, I'm not just inventing them, dreaming them up. They are literally the predictions about what an electromagnetic wave will look like. Okay, now let's talk about the speed. Speed is another really interesting feature. As I say, we call the speed C, and the speed C, Maxwell found in his electromagnetic theory, is predicted by the theory. So how fast the light ray travels through space is predicted by Maxwell's electromagnetic theory. And it's predicted in terms of two numbers that were already inside the theory and already known to the theory. So one of them was the characteristic strength of electricity, and the other one was the characteristic strength of magnetism. And one way of describing the characteristic strength of electricity is that electric permeativity, epsilon naught. And the other way, and one way of describing the characteristic strength of magnetism is the magnetic permeability of free space, that quantity we called mu naught. So if you look at this equation, I sort of love this equation, really. The reason I like it is it kind of embodies so well this joining together of electricity, magnetism, and light into one complete theory. You see, this equation only contains three things, and it's a simple combination of the three things. It contains the characteristic strength of electricity, epsilon naught, the characteristic strength of magnetism, mu naught, and the speed of light. Just those three numbers. And it just says that the speed of light is equal to the inverse of the square root of the product of the characteristic strengths of the electric and magnetic forces, the mu naught and the epsilon naught. And if you go home tonight, you know, you're a little bored or whatever, and you thought, well, let me just check this. It's worth checking this. Calculate what C is by plugging in mu naught, epsilon naught. You'll find that that speed, when you multiply those two constants, take the square root, take the inverse, is this enormous number of 300 million meters per second. So that's the speed that light travels at, 300 million meters per second. It's 186,000 miles per hour, if I remember it right. Okay, so those were some real important characteristics of electromagnetic waves. We talked about the directions of the fields. We talked about the sizes of the fields and the speed of the rays. I'm just looking in chat here. Where does the permeability and permeativity come from? Does this mean that the speed of light can't go any faster due to the nature of space it's traveling in? Yeah, that's like a brilliant question that obviously we've got another budding scientist here. So when we measure electrical interactions, we see that they have a characteristic strength, and we call it the electric permeativity. When we measure magnetic interactions, we see that has a characteristic strength. We call it magnetic permeability. But we've actually got no way of, in science, of predicting those strengths. So we actually don't know why electricity and magnetism have those characteristic strengths. And it's a real puzzle why electricity and magnetism have those strengths. And there's other numbers in our universe, actually, that we can measure the strength of other interactions. You might know of nuclear interactions. We can measure the strength of those nuclear interactions. But we don't know why they have those values, those particular strengths. And those numbers determine the nature of our universe. They determine, for example, whether we're alive or not alive, and all sorts of things like that. And we simply don't understand why they have those values. Now, given that they have those values, epsilon naught, mu naught, given we measured the values of epsilon naught, mu naught, we can predict the speed of light, and it is a single number. All light rays travel in empty space with that speed, and we can test that theory, and light rays indeed do travel at that speed. So it's a very interesting question. Can I re-explain the meaning of mu naught and epsilon naught? Yeah, so when we think back to when we wrote down the equations for the electrical force and the magnetic force due to a electrical charge or a moving charge. In those equations for the electric and magnetic forces, there were, in each case, a constant, equivalent to the gravitational constant in the gravitational force. In magnetism, that constant was mu naught. And if you made it bigger, you'd make bigger magnetic forces with moving charges. If you made it smaller, you'd make smaller magnetic forces with moving charges. So it's just a number that's in there where we measure, we observe what forces we get, and that determines that number. Likewise with electricity. We use the Coulomb constant more often, but it's related to the inverse of the electric permeability. And either of those numbers characterize the strength of the electric force. And we just measured how big an electrical force we get with certain charges. That determines epsilon naught. So that's where they come from. They just set the scale of electric and magnetic forces. If you lowered mu naught and epsilon naught, if you could do that, if you could wind them down, you'd wind down the strength of all the electric and magnetic forces. If you made them zero, you'd turn off in the universe all the electric and magnetic forces. Okay. I want to talk about the idea or the concept that electromagnetic waves carry energy and momentum. Because this might seem a weird concept that waves, like electromagnetic waves, carry energy and momentum. But actually waves, like electromagnetic waves or even sound waves and water waves, do carry energy and momentum. So we're familiar with energy and momentum from the world of particles. So particles, when I think of a particle, I think of kind of like a discrete object, a localized object. And that discrete localized object, as it moves around, can have some associated kinetic energy, can have some associated linear momentum. And we're very used to, think about back to 211 and what a fantastic time that was. We're very used to describing the energy and momentum of particles when we think about the motion and the interactions of particles. Now, when we think about waves, waves are kind of continuous things. Think of a water wave. It's all over the surface of the ocean. They're kind of not localized, non-localized things. Those waterways are all spread out over the surface of the ocean. Same for light waves, right? They're not localized at one location. They're spread out through empty space. They're non-localized through empty space. But still, they can carry and convey and transport energy and momentum. And for waves, rather than thinking about the energy and momentum of a particle, we think about the flow of energy and the flow of momentum in the wave. And in particular, what we tend to do, I hope I can give you an idea of this. So here's the light ray that came from my flashlight over here on the left-hand side. And here it is shining to over here on the right-hand side. Now that light ray, we can think of it as kind of a stream or a flow of energy and momentum. And the way that we quantify that is we imagine a surface through which that light is passing. So here's that surface. And we measure the joules per second per square meter through that surface. We measure for momentum the Newton seconds per second per meter through that surface. So with light waves, water waves, sound waves, we can't think of a particle of light waves or sound waves or water waves. We just think of this stream, this flow of energy and momentum in the light waves or the sound waves. And we quantify the description of the energy and momentum carried by the light ray or the water wave by the joules per second per square meter, or by the units of momentum per second per square meter that's carried through some surface, maybe some imaginary surface, maybe some real surface. So that's how we're going to think about energy and momentum carried by waves. Well, let's see if we can quantify that idea. So on this slide, this is about, it would have been about the energy flow in an electromagnetic wave. So this is the flow of energy in an electromagnetic wave. And we describe the flow of energy with a quantity we call intensity. And if you're a sunbather, I'm not a sunbather, I'm a sunburner. But if you are a sunbather or a sunburner, you know that sunlight carries energy, right? You can literally feel that energy as you absorb that energy. And we measure, over here on the left, we measure or quantify that energy flow with a term we call intensity. And intensity is the average rate of energy flowing per unit area, through unit area. And we would measure it in joules per second per square meter, or watts per square meter. So that's intensity. You know, a bigger intensity would be more energy carried per second per square meter. A smaller intensity would be less energy carried per second per square meter. Now, what's interesting, and Maxwell figured this out, is that intensity, that flow of energy that we give the symbol I, related to the electric field in the electromagnetic wave, or the magnetic field, or equivalently the magnetic field in the electromagnetic wave. And so this here is an equation that tells you the intensity, the watts per square meter, or the joules per second per square meter through a surface in terms of the maximum electric field in the electromagnetic wave, or the maximum magnetic field in the electromagnetic wave. So EM is the maximum electric field. BM is the maximum magnetic field. And then the other things in these equations, well, look, they're the speed of the light ray. That's the C here. And they're one of those two constants that characterize the strength of electricity and magnetism. That's the mu naught here. And so this is telling you that if you have a certain intensity electromagnetic waves transporting a certain number of joules per second per square meter, that is a reflection that inside that electromagnetic wave, inside that bundle of oscillating electric and magnetic fields, a certain strength magnetic and electric fields. So the EMs, the BMs are related to the intensities. So that electromagnetic waves, that sunlight as an electromagnetic wave carries energy, is probably not surprising to you. It's not surprising to us because we can feel that energy, feel the energy of sunlight. What might be more surprising to you is that electromagnetic waves carry momentum, linear momentum, and that electromagnetic waves can therefore exert a force on you. When they, for example, strike you, electromagnetic wave strikes you and you absorb it, that will exert a force on you. Electromagnetic wave strikes you and bounces off you, that will exert a force on you. This force of light, I could call it the force of light, the force of sunlight, is called, the term we use for it is called radiation pressure. It's the force per unit area. That's what radiation pressure is. And actually, it was a prediction of Maxwell's electromagnetic theory that light would exert force of light on things. It was a prediction that wasn't detected for a long time. It's difficult to detect the radiation pressure, and it wasn't till the beginning of the 1900s that it was detected. Now, two more equations here for light. So the momentum carried in a light ray and the energy carried by the light ray are related to one another. And again, this relation between the energy that's carried by the light and the momentum that's carried by the light comes out of Maxwell's electromagnetic theory. And I'm picturing the relation, I'm writing down the relationship here. So there's two equations here. I'm going to explain that, but gosh. I is the intensity. So remember, I is the measure of the energy flow, the joules per second per square meter. P is that radiation pressure. That's the one that's related to the momentum or the force exerted by electromagnetic waves. And so you see this proportionality in both of these equations, between radiation pressure and intensity. If the intensity goes up, the radiation pressure of the light will go up. There's constants that relate the intensity and the pressure. You see one of the constants here, it's the speed that the ray is traveling at. But then one of the equations, what I call the total absorption one, has a factor, think of it as a factor of 1 in front of the I. The other one, total reflection, has a factor of 2 in front of the I. And so these two equations correspond to these two situations. So the total absorption one is depicted in this picture here. Actually, this arrow shouldn't really be here. It's when light strikes, say, a dark object and is absorbed. Then the radiation pressure on that dark object that's absorbing the light ray is related to the intensity by this upper equation. The second picture shows a light ray actually being reflected off a shiny object, maybe a white object. In that case, the light ray bounces off the object. And in that case of reflection, the relationship between the radiation pressure, the force of the light, and the energy carried by the light is this one here with the factor of 2 in it. So those are the relationships between radiation pressure, which is associated with the momentum carried by the light, and the intensity, which is associated with the energy carried by the light. And that relationship depends on whether the light is absorbed or the light is reflected. And it kind of parallels, so imagine you're going to throw a ball at a wall. It's going to bounce off the wall. It's going to transfer some momentum to the wall. And you're going to throw a lump of clay at the wall. And you're going to throw it at the wall, and it's going to stick on the wall. So those are analogous for particles to this situation of total reflection and total absorption. When you throw the ball at the wall and it bounces off, it transfers a certain amount of momentum. It was reflected from the wall. When you throw the clay at the wall, it sticks to the wall and becomes part of the wall. You transfer a different amount of momentum. And that corresponds to the total absorption case. I want to show you a demonstration of the force of light. See if I can do that. So I'm going to share a different screen. And I hope you can see this little demonstration. So inside this glass sphere is this little sort of vein arrangement. Now, there are two white veins. You can see this one on the right here, and actually two darkened veins. You can see this one on the left here. And over here, it's hard to know what, it looks like a cannon or something, but it's not a cannon. It's actually a desk lamp. And we're going to shine light on this arrangement of these two veins, of these four veins. Now, remember that for the white vein, it's going to tend to reflect the light. And because the light bounces off it, there'll be a bigger force on the white vein. The black vein is going to tend to absorb the light. And because it absorbs the light, there's actually going to be a smaller force on the black vein. And so if you exert a smaller force on the black vein and a larger force on the white vein, you're going to get a torque. And it's going to turn this vein arrangement. And we're going to see that arrangement spin around when we shine the light on it. So let's go ahead and do that. So here I am pointing out two veins, and there are actually four veins, pointing out the lamp. And then we're going to switch on the lamp and watch the veins. Look at them start to spin. I mean, to me, this is absolutely brilliant, right? With light, we're creating a torque on that little vein arrangement that's due to the forces of the light on the individual veins of that arrangement. And so that's the force and torque of light. I'm going to do it one more time. I like this so much. Again, switch it on. They start to spin because there's a torque. It's creating turning motion. That torque's from the forces. The forces, the imbalance of forces due to one vein absorbing the light, the other vein reflecting the light. And we see them spin. And then as soon as I turn it off right, that torque goes away and they slow down under friction and come to rest. And that's the force of light. Okay, I'm going to go back to my slides. And the last property of light I wanted to mention is wavelength and frequency. So light is really, electromagnetic waves really are a whole family of different waves. Actually, let me answer before I describe that. There's a question in chat. So how does light have a force or a momentum if a photon doesn't have mass? Yeah, so that's getting a little ahead in the course because we are going to talk about photons as packets of light later on. But light is, if you think of it as packets, it is massless packets of just energy and momentum. You do not need to have mass to carry energy and momentum. And I'm going to delay answering the details of this, but light, the packets of light that we'll talk about later that are called photons are massless packets of light, but they can still carry energy and momentum. You don't need to have mass to carry energy and momentum. And light is the classic example of carrying energy and momentum, but not having mass. Okay, so let's get back from that to wavelength and frequency. I've got to get my pen going again here. Wavelength and frequency. So we've been looking at the light ray and we've been seeing the wave nature of the light wave. The electrical field oscillates like a wave. The magnetic field oscillates like a wave. So it is a wave, just like a sound wave or a water wave. And like a sound wave or a water wave have an associated wavelength and frequency. Light waves have an associated wavelength and frequency. The wavelength What is the wavelength? It tells you the distance in meters from crest to crest. So it tells us this distance here between the successive crests of the electric field or successive crests of the magnetic field. So that's the wavelength. And electromagnetic waves can have all sorts of wavelengths, from very short to very long. And what's the frequency? The frequency tells you the number of oscillations of the electric field or number of oscillations of the magnetic field per second, per interval of time. So a frequency of 10 hertz would mean the electrical field oscillates to and fro 10 times a second. Magnetic field oscillates to and fro 10 times a second. A frequency of 88.5 million hertz, that was Heinrich Hertz's generator. That means that the electromagnetic waves, the electrical field is oscillating to and fro 88.5 million times a second. The magnetic field is oscillating to and fro 88.5 million times a second. So that's the meaning of wavelength and frequency. And these terms, wavelength and frequency, we use to characterize kind of the different members of the family of electromagnetic waves. Now, there's an important equation here that the wavelength in meters and the frequency in hertz or inverse seconds are related to the speed of the light ray. The speed of the light ray is the product of the frequency and the wavelength. So since the speed is a constant, all light rays, whatever frequency, whatever wavelength, have the same speed, then if you make the wavelength of a light ray longer, you must make the frequency correspondingly smaller. If you make the wavelength of the light ray shorter, you must make the frequency correspondingly larger, because those three quantities, C, lambda, and F, are tied together by this string, this equation string, that C, the speed, is the product of lambda, the wavelength, and frequency, F. Okay, so I said that light is a family. I live in a family, you live in a family, and light rays live in a family too, but they live in a giant family, bigger than our families. So this is called, kind of obscured it here. This was meant to say Maxwell's rainbow. Maxwell's rainbow is that when he predicted electromagnetic waves, he was predicting this massive, gigantic family of electromagnetic waves, from waves that have extremely high frequencies. Look upstairs here. This is frequencies of 10 to the 22 hertz and have correspondingly tiny wavelengths. These are tiny fractions of a picometer wavelength. So these are called gamma rays. And sometimes you meet gamma rays in hospitals for treatment for cancers, can be treated with gamma rays. At the other end of the spectrum are electromagnetic waves with very low frequencies. So down here are frequencies that are kind of 1,000 hertz. That's a very low frequency. And these wavelengths are very long, correspondingly very long. So this would be hundreds of kilometers wavelength down here. And it's at this end of the spectrum that the radio waves are. You know, probably nobody knows what AM and FM are right now. But when I grew up, we basically didn't have a TV, and we had an AM and FM radio. And those waves, those electromagnetic waves, I am lying slightly here, but are down this end of the spectrum. So they're members of the family, like gamma rays are members of the family, but they've got, you know, quite different properties. And then in the middle, this is the bit I really like. there's a very thin slither in the middle from 400 nanometers to 700 nanometers. And that sliver of 400 nanometers to 700 nanometers wavelength, so right in here, it's really too thin a strip to actually draw, is visible light. You know, visible light is a huge part of our everyday lives. But visible light is just a tiny, tiny fraction of the electromagnetic spectrum of Maxwell's rainbow. And here it is. I've blown it up. Well, I didn't blow it up. The book blew it up. You see the red, the orange, the yellow, the green, the blue, the violet. That's the electromagnetic, that's the visible light spectrum. And it's some tiny fraction between gamma rays and radio waves of the entire electromagnetic spectrum. Okay, time for a quiz. Okay, I think the quiz time is up. So let me just answer this. So the question says, supposing you've got an electromagnetic wave. Supposing we double the electric field in the electromagnetic wave. We make the maximum electric field twice as big. What happens to some of the other features of the electromagnetic wave? What happens to the magnetic field? What happens to the speed? What happens to the intensity? Well, let's just go through these one by one. So speed doesn't change. Speed of an electromagnetic wave is 3 times 10 to the 8 meters per second. And it doesn't matter whether the electromagnetic wave has strong or weak electric fields, strong or weak magnetic fields. The speed of an electromagnetic wave in empty free space is always 3 times 10 to the 8 meters per second. The intensity of an electromagnetic wave, well, that's proportional, if you remember, to the maximum electrical field, or proportional to the maximum magnetic field. So if you change the electrical field, if you double the electrical field or you double the magnetic field, you're actually going to quadruple the intensity. However, if you double the electrical field, you also always double the magnetic field. Those things are proportional to one another. One way of remembering that, or seeing that, is E over B, that relationship between the strength of the electric and magnetic fields. That ratio was related to the speed of the light ray. If the speed of the light ray is constant, then if you've doubled E, you've got to have doubled B. Okay, so B doubles. Okay. Let me end the class by looking at one quick example. It's sort of a famous example. You see it in a lot of the textbooks. This goes back to the 1960s and, you know, the Cold War and the nuclear arms race. And the US had plans to build a transmitter of electromagnetic waves that were of extremely low frequency. So remember, Heinrich Hertz's electromagnetic waves were 88 megahertz. Well, this US Navy plan to create low frequency electromagnetic waves, these were 1 million times lower in frequency. They're about 75 hertz. And the idea was to use these to communicate with nuclear submarines submerged in the ocean, deep in the ocean. And so this question, having gone through all that little bit of history, which you may or may not be interested in, asks us to calculate the wavelength of an electromagnetic wave with a frequency of 75 hertz. And this is important because the wavelength sets the scale the size scale of the antenna. If you're going to detect electromagnetic waves, if you're going to produce electromagnetic waves, transmit electromagnetic waves, sets the scale of the antenna you need. So let's see if we can just calculate down here the corresponding wavelength for 75 hertz electromagnetic waves. Okay, so the master formula is over here. This is the fact that the speed of light, the wavelength of the wave, and the frequency of the wave are related to one another. C equals lambda f. And so we can obviously turn this equation around to find the wavelength, knowing the frequency. And all I have to plug in is the speed of the wave, 300 million meters per second, and divide by the frequency, 75 hertz. And if you do that, you get this enormous wavelength, about 4,000 kilometers. And so that's why this idea sounds a little crazy to me, but it was going to be so expensive. It was going to need such an enormous antenna. It's going to need so much power to run that antenna. And you had to hide it underground. Would need the scale of a 4,000 kilometer antenna. This is half the size of the Earth. Anyway, so it never got built. Anyway, that's one example of electromagnetic waves. You might want to look at them. I don't have enough time to go through them now, but I'll point them out. Two more examples. These are related to homework problems, and they might be related to exam problems. This one's about intensity and how that's related to electric and magnetic fields. This one's related about power, and that's how that's related to electric and magnetic fields. So you might want to take a look at those as you get ready for the test. Anyway, I'm going to end there. Today's class was a sort of historic class in the sort of history of science, because it did describe that joining together of an electricity and magnetism into electromagnetic theory by Maxwell, and this huge prediction of electromagnetic waves and the huge understanding that came with understanding that light is an electromagnetic wave. And so I'm going to finish there.